So let us start this morning's session. So the first speaker is Boaz Nadler. He will speak about the estimation of sparse eigenvectors.
Thank you, and thanks the organizers for inviting me. I'll tell you, estimating the sparse eigenvectors, something I've been working on for the past few years. And I'll tell you a little bit about two different works. One is with Ian Johnston, Debashi Shvod, and Aaron Birnbaum, and the other one, a more recent one, with Robert Hartgam and Danny Vinh. So, no, that's better. Manual always is better. Okay, so most people should know this, but a quick overview of what is PCA. Then we'll talk about sparse PCA, and we'll discuss two different settings. One is LQ sparsity of the eigenvectors, and then L0 sparsity. Okay, so suppose you have a random variable x, p-dimensional, there's some mean mu, some population covariance matrix sigma, p by p. You do an eigen decomposition of sigma, it has eigenvalues lambda j, eigenvectors vj, and in many applications we're interested in the leading eigenvectors or principal components of sigma, which are v1, v2, etc. And this is used for dimensionality reduction, denoising, regression, classification, etc. Of course, you don't know sigma, you don't know typically its eigenvectors. What you do get typically are n observations, xi, p-dimensional. You construct the sample covariance matrix sigma hat. You can do its eigendecomposition. And the standard approach is to use vi hat as your estimate of the ith principal component vi. And we all know a classical result that under smoothness conditions, if you have fixed dimensions, sample size goes to infinity, sample PCA is asymptotically consistent. You have convergence of the sample covariance matrix, and that implies also convergence of the eigenvectors whenever you have multiplicity 1. However, in many cases, we have high dimensional data, low sample size, and if you look at the limit as both dimension and sample size go to infinity, then various people have shown that in that case, sample PCA is inconsistent. The eigenvectors that you get do not converge to the true ones, and the paper by Johnston and Liu made this precise in some extent, or that may be one of the first papers to analyze it more closely. To illustrate this and to analyze a bit what can be done, throughout this talk I'll consider what is known as a spike covariance model with k spikes. So for simplicity we're going to consider multivariate Gaussian data, but this can be relaxed. But I'm going to assume that my matrix sigma has k signals, lambda 1 up to lambda k. Everything else is 0, and actually it should not be diagonal. This is after the diagonalization, so there is a basis W of eigenvectors that make it diagonal. And for this model, just to illustrate the fact that sample PCA is not consistent, you can in this limit compute what is the overlap between the ith principal vector and the true one. And you have this formula. There is a phase transition. If the signal strength is below some quantity, there are simply directions which are pure noise, which have larger variance than the ones of the signal, and if not, you get some formula here. And again, the important thing is that if you take this formula, look what happens at small noise level sigma, you get this kind of Taylor expansion. You see here the effect of P over N. If P over N is large, this can be non-negligible. The overlap can be far away from 1. This formula graphically looks like this. This is the overlap. Up to square root of P over N, there's no overlap. You just get a random direction uncorrelated with your signal, and then it slowly starts to go to 1. So that's the starting point of my talk. Can we do better if we assume some sparsity assumptions on the eigenvector? Because, for example, in this region, what you get is a direction due to pure noise which has a large variance, but that direction is highly non-sparse. It's just a lot of random entries. And if what I'm doing, if what I want to do is to search for a sparse direction with high variance, maybe I can do much better. So, in other words, if you assume that the k leading eigenvectors are sparse, then we can ask how well can we estimate them. And as I've said, I will study this a bit in two different settings. One is approximate sparsity, so we're going to assume that the eigenvectors belong to an LQ ball with radius C. And then we'll also discuss a bit the case of exact or L0 sparsity, where there are exactly k non-zero entries in the leading eigenvector. Okay. So some theoretical questions you can ask for in this case is minimax rate of estimation. Are there computationally efficient methods that achieve these rates? And also we'll see that what if there is a difference between LQ sparsity and L0 sparsity, and if so, what it is. Okay, so there have been many papers on sparse PCA, algorithms, analysis, optimization. One of the algorithms suggested by Ian Johnston and Arthur Lowe is the following, very, very simple. Very computationally efficient. First, you don't compute the whole covariance matrix P by P. You only compute its diagonal entries. You threshold, you select only those which are very large. And then you compute only the covariance matrix on these coordinates, and you do its eigendecomposition. So the complexity of this method is order of Pn squared, because you need to compute P entries like this. Each of them is n squared. And then, so each of them is order n. And then you have to do an eigendecomposition of this, but you assume that this is much smaller.
Constant size.
Assuming that this is much smaller than n, then yeah, this is wrong. It should be Pn plus order of k cubed. K is the size of that. Yeah. But it's much better than BQ. So the question is whether this extremely simple procedure is rate optimal for example. So here is one result that we obtained with Aaron Birnbaum, Ian Johnson, and the Bashish ball. So first of all, we have a lower bound on the minimax risk. If you have an LQ sparse vector V, there are some additional conditions here that I'm not stating, they're in the paper. But in general, you get this lower bound on the rate of estimation. And you can also show that if you do diagonal thresholding, then there exists a vector in LQ. You can just construct it and show that for such a vector, diagonal thresholding will incur a risk which is larger than something like this. It's a different constant C. But notice that the rate is much worse. Here it's 1 minus q over 2. Here it's only half of that. In the next slide, I show that this rate is indeed achievable. So this is not only the lower bound, this is the minimax rate, which means that diagonal thresholding, although it is extremely efficient, it's not rate optimal. I also mentioned that there's related work by Zong Min Ma and by Wu and Lei with similar results. Okay, so maybe a little bit of some intuition why this method is not rate optimal. So what does this method do? It looks at the diagonal entries and chooses those that are above some threshold. Now, this threshold, you have to choose it so that you avoid too many false detections if you have just entries which are pure noise. So it has to be essentially of this form. But if it has to be of this form, then this method can detect weak signal coordinates which are only as large as this quantity. And if you do the analysis, you see that to get the minimax rate, you want to choose signal coordinates which are much, much weaker. Okay? Now, what this means is that in your P by P matrix, you looked only at the diagonal, there's much more information in the off-diagonal entries, and you somehow need to look at it, maybe to be able to extract such coordinates. You are able to do it in some settings. Let me give you a simple two-stage algorithm that does it. So the first stage is you run diagonal thresholding. You pick a few coordinates which are really strong. You do an eigendecomposition of the matrix with these first selected coordinates. You keep the first few leading eigenvectors and eigenvalues of this matrix. And now you want to pick up additional coordinates which were strong, but not sufficiently strong to be picked up by the first step. Then you simply look for coordinates which have high covariance with one of these eigenvectors. And then you just do an eigendecomposition on the larger set of selected coordinates, and you can show that under certain conditions this algorithm achieves the minimax state. So zone minima has a different estimator, somewhat similar, but also it proves that this estimator also achieves the same rate. So the lower bounds on the minimax rates are indeed the minimax rates. One more thing, it's interesting to compare sparse eigenvector estimation to sparse covariance estimation. So a matrix which has sparse eigenvectors is a particular case, or a matrix which is generally sparse. And if you have a sparse matrix, then Bickel and Levina and Tony Kai and many others have shown that the minimax risk for estimating the whole matrix is of this form. And the key point I wanted to make was that this problem and sparse PCA are different problems. The minimax rate here, which is 1 minus q, is worse than the minimax rate for the eigenvector estimation, which is 1 minus q over t. Okay? So, okay. Okay, so that was the first part of the talk, and now let me move to the second part. What if you want to estimate an exact L0 sparse eigenvector? So let me give a teaser. We know that many problems in L0 are NP-hard. Let's see what happens in this case. So one interesting paper by Amini and Wainwright a few years ago looked at this problem and what can be thought as the hardest case in the L0 ball, where a vector V has k entries, and they're all of equal magnitude 1 over square root of k. And we looked at the problem of support recovery, finding the entries which are non-zero. And he proved that as n go to infinity, you cannot recover the support unless your number of samples is at least of this form. And he showed that if you look at diagonal thresholding, then you'll need at least this number of samples, different constants. But the key point is that here we have k, and here we have a k squared. So if you think about, let's say, a really high-dimensional problem, and k is 100, it seems that here you're going to need 100 times more data points, more samples, to be able to recover a weak spike in noise. And an interesting question is that the interplay between statistics and computation is whether there exist computation efficient methods that close this gap. And one approach to try to recover sparse PCA, it's a very nice paper by Jasper Monk who's here, and Mike Jordan and others. They relax the L0 sparse, the L0 constraint which is non-convex, to an L1 type constraint for the whole matrix X, and they try to maximize the trace of sigma hat X. big X is now a P by P matrix, and this problem is solved by an SDP, and you hope that this big matrix X is rank 1. If it is rank 1, then trace of sigma hat big X is just the trace is just equal to a V transpose sigma hat V. So you just found a vector V that has large variance and is A1 sparse in some sense. And for this method, Amin Wainwright in the paper had the following theorem, that if the SDP is rank 1, then this is more or less their words, then SDP is statistically optimal. It is able to recover the support with number of samples n of this form. And this result seems to close the gap between information and computation. They also write in their paper that they do show that the SDP is rank 1 in a somewhat different regime. So maybe by extension, it's also rank 1 here, and we're done. Which is very nice. The only thing is this if that they put here in red, and there's a purpose to that, because, as I've said, L0 type problems are typically NP hard. So you can ask yourself, is the SDP solution indeed rank 1 up to the information limit? Maybe up to, let's say, just a factor. Okay? Let's relax it to something. It's close to rank 1. Then we're going to allow a little bit of noise to get in. So let's assume its largest eigenvalue is close to 1. What is the relation of the leading eigenvector and the true signal? And before I continue, let me mention some recent work of Philippe Rigolet with Berthet. Actually, there are two works. One studying the issues of detection, not estimation, but just detection. There is a sparse spike. And a different work that shows an equivalence between sparse PCA and a problem well studied in the computer science literature of a hidden click. So the result, and I hope I quote it more or less correctly, that if there exists, there should be a randomized polynomial algorithm to detect a spike with sparsity level k much larger than square root of n, then that algorithm can also detect in polynomial time a hidden click of size much smaller than square root of n. So what is in a random graph? So the hidden click problem says you have a huge random graph, g n half, so n nodes, and you connect two nodes at random with probability half. And a hidden click means that inside this graph you choose r nodes at random and you connect them with probability 1. So you put a hidden click in there, and current methods are able to detect the hidden click only of size square root of n and above, and the hidden click problem is believed to be computationally hard. So this result suggests that maybe the SDP cannot be a rank 1. If it would be rank 1, Amin and Wainwright implied that it would recover the support. It would recover the support, it could also solve the hidden click problem. Okay? So, in joint work with Danny Vilenchik and Robbie Krafthammer, we studied this problem a bit. Now let me tell you a little bit first about the challenge. So we want to say something about the solution of this SDP problem, but the SDP is a highly nonlinear, although convex, but highly nonlinear problem. I don't have a closed form solution for its closed form expression for its solution. I still want to say something about its value and its relation to the eigenvector, etc. So that's a challenge. Nonetheless, we were able to show the following. So consider a limit where both p, n, and k go to infinity, dimension, sample size, sparsity level. P over n goes to some constant c. The sparsity is much smaller than n, but larger than p over square root of n. Then if your spike strength is smaller than square root of c, this is exactly the phase transition to be detected just by standard PCA, I can tell you that the value of the SDP at an optimal solution is bounded between these two quantities. Okay? The right-hand side is easy. That's just the largest eigenvalue of sigma hat. So this is just removing some of the constraints. For the left-hand bound, you have to work some more. What you do is look at the part of the matrix that has just the noise. And you show that if you normalize it correctly, it satisfies the conditions and it has this value, at least. So, for example, if P over n is much larger than 1, you're in a really high dimension small sample size, these two are essentially very close to each other. Okay, so that's one result. The second result is, okay, I don't know what is x optimal, I know that its values between these two quantities. What about, can x optimal be rank 1? So we have a different theorem that says that under certain conditions, any rank 1 feasible matrix, it has to satisfy the constraints, has an SDP value smaller than 0.6 times P over n. So the optimal value is, we have probability larger than P over n. Any rank 1 matrix is below 0.6 P over n. Though combining these two, you get the conclusion that the SDP solution cannot be rank 1 up to the information limit. There exist parameter values or parameter settings where the SDP is not equal. Okay, so fine, maybe it's close to rank 1. So suppose the matrix X is almost rank 1. So what do? How do you extract the sparse eigenvector? You do the eigen decomposition of X, sum of lambda j, Vj, Vj transport. And a sensible approach is to say I'm going to take V1 as my estimate of a sparse eigenvector. So another result we're able to prove is the following, that if you do this procedure, I called it W1 here, then the overlap between W1 and the true spike is bounded by something like this, with some order 1 constant. And again, you see that if P over n is much larger than 1, this will not, that's not a full proof, but it means that this vector is not perfectly aligned with the eigenvector V. So, yeah, the large eigenvector is quickly related to the sparse vector. So, if I combine all of the above results, this is trying to give you an overview of this problem. The x-axis is the sparsity level. The top row is for estimation. The bottom row is for detection. If the sparsity level is below n over log n, everything is up to constants. It's just a high-level description. Here, diagonal thresholding works. This is where you can prove that the SDP is rank 1, but you don't need to invoke the SDP. You can do diagonal thresholding in this region. If the sparsity level is larger than n over log n, I mean, in Wainwright proved that estimation is not possible, and Rigolet proved that detection is not possible, somewhat not surprisingly. In his paper, Bertin Rigolet, in this region, show that you can have computation efficient detection up to sparsity levels of square root of n. And here they show a relation to the hidden click problem. Our work showed that the SDP is not like one in this region. And there is a small region here where it's not yet exactly clear if you can do support recovery computation efficiently. What we've observed is that with a simple covariance thresholding algorithm, so not diagonal thresholding, but just the Bickel and Levina covariance thresholding algorithm, first it works much better than diagonal thresholding for L0 sparse. Yeah.
That was for P larger than n, right?
What this?
Yes.
This is assuming P is n, let's say, or something. There are 4 parameters in the problem: P, n, k, and the signal strength.
Right.
So I'm trying to give you I'm trying to compress it
somewhere
into one dimension.
Yeah,
so
yeah.
It should be P, what is it? It should be log n should be log P, and okay, so yeah, but think about P equals some constant times n. Everything is up to constant.
Power of n, actually. It's all in the log, right?
Yeah, I agree, but yeah, as long as it's not exponentially. So a covariant thresholding algorithm works much better than diagonal thresholding. It's also very computationally efficient. And when we run it and scale it with the sparsity level k, as we increase n, we see that at least empirically, it seems to scale like square root of n. So it may close the gap where I put the question mark.
What does it look like when you scale it with square root of n or log n?
So actually, it goes a bit here, so it may be better. There may be even some log factors, but that needs to be proven. That's for future work. We do want to put up a conjecture following our work and that of Philippe, that there is no conjecture. There is no computationally efficient method that can recover an L0 sparse spike for sparsity levels much larger than square root of n, maybe up to factors. And that's it. I think I finished my time. So, as we all know, in many contemporary applications, we have high-dimensional data. We looked at the problem of sparse PCA, provided minimax risks in LQ, a foundation efficient algorithm to achieve it, again, for LQ sparsity. One word of caution: if you want to run it on actual data, the thresholds have to be carefully tuned. Log P has log P and various such terms hidden in there. And again, an interesting question is this interplay between computation and statistical efficiency. I've been working on this on other problems as well. I think this is a question that is of great interest. There are some papers on the website. Thank you very much.
So, one quick question.
How do these lower bounds translate in terms of support recovery? Because that's all you care about, right? Because you can always run PCS a second time.
So I don't have a...
Okay, so it's important for certain people.
No, empirically, first of all, as you may know, you should know that it's very difficult to run the sparse PCA, the SDP for large.
Right, no, what I mean is in terms of the negative results on the...
So I don't,
estimation.
beyond the...
your real test is...
Beyond this result,
yeah, exactly.
I cannot tell you that it's exactly zero. My conjecture is that in these parameter ranges, what you get is something which is totally irrelevant and it's zero. But that I'm not able to.
I think what he wants to see is something that says that the Hamming distance between omega 1 of
yeah.
is strictly larger than 1.
Yes.
Yeah, so I'm claiming that it's probably K.
Okay.
Or 2K, depending on how you measure.
But
but that I'm not able to prove because, again,
because you agree that in the end this is what matters, right?
I agree.
If you
So I agree. So there is a gap here. Empirically, we observe that you cannot recover the support, but I'm not able to rigorously prove it because, again, I don't know how the solution looks like.
Yeah.
I want to comment the Hamming distance is the poor man's distance. Second, the other thing I wanted to say is here you tried to say that it was approximately rank 1 and you wanted to see if it was robust to that. I wanted to know if the Amini-Rin rate result is also robust to approximately rank 1 solutions or not. Like, do they say that if the rank 1, if the SDP is approximately rank 1, and then I round it to a rank 1 solution, am I getting something that is good, that has good support recovery? I mean, I'm pretty sure they don't say it, but can we work their proof to get this kind of result?
So A, as far as I remember in their paper, they say that if it's not rank 1, let's extract the leading eigenvector as I did here. In B, they don't have any theoretical result on what about it.
Okay, thank you very much.
Thank you.